Okay, back at it again. Today we're going to be looking at pipes. Pipes can also produce standing waves, just like strings could. A couple major differences are the velocity, where in a string you have to account for tension and length and mass. When it's a pipe or a wind instrument, all you have to account for when talking about velocity is the temperature of the air which the thing is being played at. We will always use 343, which is the speed of sound at room temperature. So this is the velocity of sound in air. Now if we change medias and put it through metal, sound can actually travel more quickly. For example, if you wanted to listen to a train, you could actually hear the train in the train track before you would hear it in the air, and that's because sound travels more rapidly in metal because it's more elastic. Underwater, you can hear boats underwater before you see them for the same reason. Uh, the speed of sound in water is faster than air. But this is the one we're going to use. So that makes it a little bit easier, in fact, because you don't have to run through a formula at the beginning to figure out how quickly um, the waves will travel. When we're talking about a wind instrument, like a pipe, then that's all you have to worry about. Now, there is a concern, though, with pipes, and that's the fact that pipes can have openings at both ends, or a pipe can actually be set up so that it is closed at one end. Now, an open pipe is a lot like a string because it will have nodes on each end of the pipe. And a closed pipe is something totally new. And the reason that's going to be totally new is because it's going to end in an antinode. So what happens is you're producing some frequency here. You're producing highs and lows, and we start with the node, and then it would come down and end in the antinode. Just like before, we get what we call the first harmonic, fundamental frequency. Then we get our second harmonic forming, and then we get our third harmonic forming. And there's more harmonics than even this. You can have 7, 10, 12 harmonics, but I'm only going to hold you accountable to the first three. So that's the way that it would look for the first three harmonics. In a closed pipe, once again, it starts just like you would expect with a node, but it ends with an antinode. So now we're forming shapes that kind of look like this. For the first harmonic, always have to end like this though, okay? But you got to throw in another node, so we throw it in here and we get this much of a wave. That's actually called the third harmonic, so that's a bit tricky, the fact that that's the third harmonic. And this they call the fifth harmonic. And it has 3 nodes like that. Now I know it looks like a jumble, but I'm going to break it up and we're going to look at each one independently of the other, and we'll do an example for each. But at the beginning, that's kind of what we're going to be dealing with here, is this concept of nodes and antinodes and how we get wavelengths from that. So let's talk a little bit about a pipe that is open. And the only bit of information I give you about the pipe that is open, I turned it on its side also, is that it has a length. This is the pipe, 4 meters long. So like a pipe from an organ or something like that, for example. And in this pipe, because it's open, this is guaranteed. Starts and ends with a node, just like we saw for a string. And then we're going to start to form our harmonics. So the longest wave will look something like this. And the wavelength is actually longer, so this dotted portion doesn't happen, but that's what it would look like for the complete wave. So how much of a wave do we see for the first harmonic in an open pipe? we see half of a wave. When we algebraically rearrange that, we see the wavelength is equal to 2L. Then let's continue here and talk about the second harmonic. So the second harmonic starts with a node, ends with a node, and then there's a node in the middle. So we get something that kind of looks like this. Okay, and that would be the same thing as saying L equals 2/2 wavelengths, or wavelength equals L. So the length of the pipe is one wavelength for that example. For the third harmonic, for an open pipe, we have to throw in an additional node, and it would look something like this. And so when you say how much of a wave is that, that's more than a wave. So L equals a total of, if you look at this, this is going to be 1.5 waves. Another way to say that is 3/2 of a wave. So 3/2 a wave, wavelength equals 2/3 L. That's kind of small. See if we can clean it up a little bit. All right. So oftentimes when we represent drawings of the pipe, though, the way that we'll represent the drawing is we kind of show the pipe and we show where we have a lot of pressure and places where we wouldn't have a lot of pressure. So these would be like your high pressures and your low pressure, or low displacement and high displacement. So when you see my drawings of the pipe, it'll look more like that, and there will be some rectangles that you can fill in on the problem set as well. So this one looks kind of like this. And then this last one looks a bit like this. So you can kind of see, and sometimes you fill in the middle too. That makes more sense for a string, but if you want to, you can. It doesn't really matter. Okay, but that's how you represent the first 3 harmonics for an open pipe. And then when I bring back our original drawing, when you put all these on top of each other, that's when you get that shape right there for the open pipe. Now, if we take a look at another pipe, well, we can go ahead and we can do the math for it while we're here, I guess. So I told you that the length of the pipe was 4 meters. So that means it would have a wavelength, if we just multiply that, of 8 meters. And for the second harmonic, it equals the length of the pipe. So the second harmonic has a wavelength of 4 meters. And then the third harmonic, 2/3 times 4, or 8/3, or 2.67 would be its wavelength. I better confirm that. So we'll do, this is an easy way to kind of work with fractions in your calculator. Yes, 2.67. All right, so those are our wavelengths, and then we can use this formula right here, V equals frequency times wavelength, and we can solve for our frequencies. So I could put in 8, I could put in 4, I could put in 2 2/3, and then I could put in V. Now keep in mind, as I talked about at the beginning, V will be 343. So we put in the velocity of sound in air, and it will be 343 for all of these examples, and then we can solve for these 3 different frequencies. Now these 3 frequencies have names. We can call the first one the fundamental frequency. We can call the second harmonics frequency the first overtone, and we can call this one the second overtone. So the third harmonic is the second overtone, and that's really no different than what we saw yesterday. So if I take 343 and I divide by 8, I get pretty much 42.9. So that's my fundamental frequency, 42.9. And then I can do it for the first overtone. So I can take 343 and divide by 4. Notice that I'm getting twice as much because it's the second harmonic, 85.8, let's say. And then if we divide by 2 2/3, we get this last number for the second overtone, 128.5. So basically, we went through and we just multiplied that original number, which was 42.9, by 3. And that's how we came up with the third harmonic. And it works the same way for the second harmonic. You take the fundamental, the first harmonic, and multiply it by 2, and you get the second. So that's how it works for an open pipe. Let's take a look at a closed pipe now. So I'm going to use the same length of pipe, 4 meters in length, let's say. The big difference is it's closed. So how's that going to change things? Well, the big difference, we still start with a node, but we end with an antinode. So when we go to represent our waves, the first wave we draw is huge, like larger than this paper, because 4 meters only gets you 1/4 of a wave. There's all of this wavelength here that we can't really see. And then it would like continue on over here onto this other piece of paper, and it would take a whole lot of paper to actually get one wave. So what we see, or what is represented here for our first harmonic, is you're seeing 1/4 of a wave. L only equals 1/4 of a wave because it went from node to antinode and then stopped. Then for the next harmonic, which is actually called the third harmonic, you'll see why in a second. I guess I should use my colors that I used last time. For the third harmonic, you're going to start with a node, you're going to end with an antinode, where we're going to put another node in its place. So we might draw it looking a bit like this. And so how much of a wave is that? Well, we're missing this piece right here. So we're missing this piece, so that'd be 3/4 of a wave. So L equals 3/4 of a wavelength, or wavelength equals 4/3 L. Now, I mentioned I would explain where the third harmonic comes from. It comes from the top number here in this fraction. Just like last time, the first harmonic came from the top number here. And so then we have to throw in an additional node. So when we do that, this is all within the same length of pipe. We start with a node, and we do an anti, then we do a node, then we do another node, and then we finish with an antinode. So you get like a wave that kind of looks like this within that pipe. And you're wondering how much of a wave is that? It's actually more than a wave. This would be one wave, and then we've added on another 1/4. So the best way to say that would be L equals 5/4 of a wavelength, or wavelength equals 4/5 L. So the top number is a 5, and so you guessed it, it's called the fifth harmonic. Fifth harmonic. So a closed pipe doesn't go 1, 2, 3. A closed pipe goes 1, 3, 5. So if I want these to look kind of like it does inside the pipe, I would kind of continue on out like that. And then if I want to represent what it looks like inside the pipe, I would continue it out for that. If I want it to look like it does inside the pipe, I continue it out for that. Fill in that action there. Okay? Now, you can kind of see why in the original picture I drew, I made it kind of look a bit like that. Because all three of these and even more are occurring at the same time in the pipe. So it's very complex. But if you superimpose these on each other and throw it in the pipe, that's what you would get. So let's deal with the math now. Like what are the wavelengths and what are the frequencies created for the first three harmonics? So when dealing with that, we have to kind of use the rearranged equations and the length of the pipe. So in this example, I said the length was 4. We would get wavelength is equal to 4L. So if wavelength equals 4L, and L is 4, 4 times 4 is 16 meters. I told you it was a really long wave. Then if we want to find the wavelength for the next one, wavelength equals 4/3 L. So we put in the length of the pipe, 4, and we get 16/3, which is 5 1/3, or 5.33 meters. Then for the last one, what we have is we have wavelength is equal to 4/5 L. So L in this example is 4, and we would get 16/5. And that's going to be 3 1/5, which would be like 3.2 meters long. All right, so these are our wavelengths. Now remember, wavelengths aren't frequencies. We're going to want to find the frequencies. So this is called the fundamental. This one's actually called the first overtone still, OT, overtone. And then this one is called the second overtone. So those names don't change, even though the names or numbers of the harmonics change. So, like we talked about last time, if V equals frequency times wavelength, and now we know our wavelengths, and we know V is always 343, we can then solve for our frequencies. So it's going to take a little bit of a calculator work to get this figured out. So we want to take 343 and divide it by our wavelengths. So I get 21.4 for the fundamental, 21.4 hertz. For the first overtone, or third harmonic, I divide by 5 1/3. And I end up with 64.4. So I'll fill that in, 64.4 hertz. Last but not least, the second overtone, or fifth harmonic, and we divide by its wavelength, 3.2, and we get 107.2 hertz. So if we stop and we kind of compare these frequencies, you'll start to see a little relationship develop here as well, based on the number of the harmonics. So if we take the fundamental and we multiply it by 3, we get the third harmonic. And if we take the first harmonic, or fundamental, and we multiply by 5, we get the fifth harmonic. That's the quick and easy way to do it, although you don't have to do it. So to recap, the big difference between pipes is the sound, its velocity, is the velocity of air, which is always 343. We have different ways to represent these standing waves inside the pipe. It's very complex. If you work them out individually as different harmonics, it can make it a bit easier. We use V equals frequency times wavelength, and then the length of the waves to find wavelengths and frequencies. It's kind of complicated. You'll have to practice it a little bit before I think you get it down for sure. But that's where we'll stop today, and we can work on it in either recitation. We can also work on it if you email me questions. All right, thanks for watching.